Hi everyone, I am Abdulaziz Abdullah, a master's student at Ankara University's Chemical Engineering Department. Today, I am excited to present our research on the catalytic effect of zirconium-loaded ZSM-5 dope beta catalysts in the transalkylation of 1-methyl naphthalene and toluene 4,2,6-dimethyl naphthalene and p-xylene synthesis. I want to acknowledge my supervisor, Professor Dr. Ali Karaduman, and also the organizers of this conference for this opportunity. Thank you for being here. Let's begin. Before we go into the details of the presentation, I would like to provide a brief outline and overview. Firstly, I will discuss the context and motivation behind this study, and then we'll look at the specific goals we set to achieve from this research. Next, I'm going to talk about the methodology and procedures used in the experiment, and then we will discuss the results and outcomes of the experiment. Finally, I will summarize our key findings and highlight their significance in the broader context of catalysis. Let's start with a brief background of our research. Plastics, as we all know, have become an indispensable part of our modern society. Polyethylene naphthalate, or PEN, has emerged as a promising alternative to the widely used polyethylene terephthalate. It has exceptional mechanical, thermal, and barrier properties, which makes it a material of great interest in several applications. Another key player in our research is p-xylene, which accounts for 80% of the global xylene demand. It holds significant importance as a fundamental building block for many polymers. 2,6-dimethyl naphthalene is also a crucial starting material in the synthesis of PEN. However, the current large-scale production of PEN involves a complex series of steps, which contribute to increased cost and environmental concerns. Our research aims to address this challenge and explore a more efficient and sustainable approach. Now, let's look at the significance of zeolite in our research. Zeolites are widely known crystalline aluminosilicates with molecular size pores and acidity, which makes them exceptional solid catalysts. Several studies have shown that small and medium pore zeolites, while highly selective, restrict the diffusion of larger molecules. Our focus in this research, however, lies on the use of beta zeolite, which features 3D larger pores and abundant mesopores, which are known for their excellent catalytic activity. Our research also aims to investigate metal loading on zeolite and its interaction with reaction parameters in 2,6-dimethyl naphthalene synthesis. To optimize our processes, we would employ response surface methodology, a statistical approach which is a less explored aspect in the literature. As part of the objectives, we sought to synthesize zirconium-loaded ZSM-5 dope beta zeolite catalysts to establish the foundation of our catalytic process. Secondly, we sought to understand the relationship between reaction temperature, weight hourly space velocity, and metal loading in the transalkylation of 1-methyl naphthalene with toluene. Finally, we sought to identify optimal catalyst and reaction conditions for maximizing 1-methyl naphthalene conversion as well as 2,6-dimethyl naphthalene and p-xylene yields. Now, I will briefly outline the methodology and some procedures we undertook as part of the experimental section of the research. We began by obtaining the ammonium form of zeolite beta and ZSM-5 from zeolists, which was calcined to obtain their 8 forms. Different zirconium weight percentage catalysts were then prepared through a wet impregnation procedure as illustrated in the figure. This involved impregnating the H-form zeolite with an aqueous zirconium salt solution at 50 degrees Celsius for 24 hours. The metal zeolites were subsequently dried, pelletized using gamma alumina as a binder, and finally calcined to obtain the required zirconium catalysts. We employ several characterization techniques such as XRD for the structure and phases present, SEM to examine the morphology and metal distribution, XRF for elemental analysis, and pyridine FTIR to assess the acidity of the catalysts. The experimental setup, as depicted in the figure, comprised a fixed bed reactor, a feed mixture consisting of 1-methyl naphthalene and toluene in a 1:1 ratio, the use of nitrogen as an inert carrier gas, and a dedicated section for product collection and GCMS analysis. Before each test, the catalyst was activated at 500 degrees Celsius while maintaining a continuous flow of nitrogen gas. A box banking design at 3 levels was employed for the response surface study on zirconium-loaded zeolites. This method allowed us to systematically vary and examine the effects of the independent variables on 1-methyl naphthalene conversion as well as 2,6-dimethyl naphthalene yields. Moving into the results and discussion phase, let's first focus on the characterization of the zeolite catalysts. As seen in the figure, nitrogen sorption isotherms for all zeolite catalysts displayed IUPAC type 4 behavior with an H1 hysteresis. Notably, the impregnation of zirconium on the zeolite catalyst had distinct effects on its properties, which are shown in the table. It was observed that there was an increase in micropore volume and a decrease in surface area. However, the pore diameter remained relatively unaffected. These observations are crucial for understanding the changes in the catalyst structural properties and have a direct implication for its catalytic activity. In addition, XRD analysis confirmed the coexistence of MFI and BEA zeolite phases. When XRD patterns of the catalyst were analyzed, distinct peaks at 31.9, 44.6, and 57 degrees, which correspond to those of tetragonal zirconium oxide phase, provide insight into the composition and structure of the prepared catalysts. Next, the types and amounts of acidity present on the catalyst were determined by FTIR adsorption of pyridine. Bronsted acidity are generally accepted to be the active site for transalkylation. However, high density or strength of this site leads to the formation of undesired polyaromatic compounds. As shown in the figure and in the table below, it was observed that zirconium impregnation reduced Bronsted acidity by deprotonating the Bronsted sites while also generating additional Lewis sites. This tuned acidity is crucial as it prevents the formation of undesired multi-alkylated products like trimethylnaphthalene and tetramethylnaphthalene. Moving on to catalytic activity, let's discuss the performance of the catalyst under various reaction conditions. The unmodified ZSM-5 beta catalyst displayed notable characteristics such as a high 1-methyl-naphthalene conversion at elevated temperatures. However, as the weight hourly space velocity increased, the conversions declined. The highest conversion of 54.1% on this catalyst was achieved at 500 degrees Celsius. From the model equation and the response surface presented below, a clear trend emerges for zirconium-loaded catalysts. It can be seen that increasing zirconium loading on ZSM-5 beta catalysts of up to 5% led to an improved 1-methyl-naphthalene conversion while maintaining a constant reaction temperature. The peak conversion of 63% was achieved with 5% zirconium loading at 500 degrees Celsius. This result underscored the important interaction between zirconium loading and temperature on conversion. Now, a look at the effect of temperature, space velocity, and zirconium loading on 2,6-dimethyl-naphthalene yield. From the results of the catalytic tests, it was observed that temperature and space velocity were the significant parameters that affected the 2,6-dimethyl-naphthalene yield. Interestingly, at a lower space velocity, there was no significant change in 2,6-dimethyl-naphthalene yield as temperature increased. However, at higher space velocities, a linear increase reaching up to 2.2% at 500 degrees Celsius was observed. Additionally, it was found that a 5% zirconium metal loading enhances 2,6-dimethyl-naphthalene yield. Nevertheless, increasing space velocity and metal weight percentage beyond this had a negative effect as seen on the response graphs. The lowest 2,6-dimethyl-naphthalene yield recorded on the zirconium catalyst was 1.3% at 400 degrees Celsius, while the highest value reached was 3.7% at 500 degrees Celsius. Moving forward with the discussion on catalytic activity, let's focus on the production of p-xylene. The experimental results demonstrate a clear trend. P-xylene yield generally increases with temperature. The highest p-xylene yields were both obtained at 500 degrees Celsius, with a 4.6% on ZSM-5 beta catalyst and 6.7% on zirconium ZSM-5 beta catalyst. Upon careful examination of the coded model equation given below, we observe a linear relationship between p-xylene yield and two key factors, that is, temperature and zirconium loading. It is important to note that the impact of variables on p-xylene yield follows this order. Firstly, temperature, then zirconium loading, and lastly, the space velocity. These insights into the factors influencing p-xylene production are crucial for optimizing the catalytic process. Here we present a GCMS chromatogram from the analysis of the reaction products. To summarize and compare the catalytic activity on both catalysts, it was seen that the highest 1-methyl-naphthalene conversion, 2,6-dimethyl-naphthalene yield, and p-xylene yield on unmodified ZSM-5 beta zeolite were 54.1%, 2.2%, and 4.6% respectively. By leveraging the box banking design experimental approach, the introduction of zirconium onto the ZSM-5 beta catalyst led to notable improvements. 1-methyl conversion increased to 63.1%, 2,6-dimethyl naphthalene yield improved to 3.7%, and finally, p-xylene yield significantly increased to 6.7%. These improved catalytic activity were all achieved on a 5% zirconium catalyst at a space velocity of 1 per hour and a temperature of 500 degrees Celsius. To conclude the presentation, this research began with an attempt to investigate the effect of zirconium impregnation and its interaction with reaction parameters in the production of 2,6-dimethyl naphthalene and p-xylene on ZSM-5 doped beta zeolite catalysts. Through the catalytic experiment, it was observed that catalyst activity, measured in terms of conversion and yield, generally increased with increasing temperature but decreased with higher space velocity. The strategic tuning of the properties of the zeolite and its synergy with the loaded metal played a pivotal role in enhancing conversion and yield, while effectively preventing the formation of undesirable products. Notably, zirconium impregnation led to a significant improvement in 1-methyl naphthalene conversion, increasing it from 54.2% to 63.1%. By utilizing a box banking design and response surface methodology, the optimum reaction conditions were identified as a space velocity of 1 per hour and a temperature of 500 degrees Celsius on the 5% zirconium ZSM-5 beta catalyst. These conditions yielded 3.7% 2,6-dimethyl naphthalene and 6.7% p-xylene, compared to 2.2% and 4.6% respectively on the unmodified ZSM-5 beta catalyst. This study provides valuable insights demonstrating that zirconium loading enhances catalyst properties by offering alternative pathways to achieve higher yields and selectivity. Thank you once again for your attention, and any questions or further discussion on the research is welcomed. Thank you.